All right. Good afternoon. My name's Edmund, and I'm going to talk about tries and also Burstsort. The agenda for this brief talk is first I'll motivate and illustrate what the trie data structure is, then implement one, a standard simple trie with JavaScript, and then introduce Burstsort. Burstsort is a sorting algorithm, but this is a talk about data structures. So to motivate it, I'd like to begin with a challenge. Find a data structure for storing strings that allows for fast insertion, search, and deletion. A knee-jerk reaction might be to say just use some arrays. After all, if we know the index value of the strings in the array, lookup time is constant time. And if the arrays are short, then we have some simple search, find, insert, and deletion methods that we can use. But for this, let's assume that we don't have the index value, and the kind of array, the number of strings we're working with is very, very large. To illustrate this, if we are dealing with many strings, we might have to store strings like this in our array. And you'll notice if we have string and stringent and stringify, etc. in our array, we are repeating ourselves an awful lot. All of these strings share the common prefix str, and 4 of them share the common prefix ing. So what we could do, if we're very clever, is take advantage of the structural similarity among all of these strings and build a tree out of them that would look something like this. So all of these strings that have a common prefix str grow out of that prefix, and then all of the strings that share the common prefix ing grow out of that one. If we rotate that 90 degrees, we get what's called a trie data structure, and it looks like this. If you read through it, you'll see that we have lies, listen, listed, listless, lists, and strong, stringify, strings, and stringent, all stored in a tree-like fashion. To illustrate the usefulness of this data structure, I'm just going to walk through a couple methods. First, the find method. What would we have to do to find listened in this trie? Well, all we have to do is iterate through the word we're looking to find and map each character to a path on the trie, like so. We stop at n and we see that there is a path for the word listen. Is there a path for E and D, the last characters of listened? No, there isn't, so we say that the string is not found in this trie. To insert, all we do is, again, iterate through the word we want to insert and map each character to a path in the trie. There's a path for listen, there's no path for E and D, so we unlock new nodes, E and D. As you might have surmised, the insertion and find time complexity for a trie is O of n, where n is the length of the string we're looking to insert or to find. And if we assume that there is a maximum length to the strings, let's say the English language, there's not going to be a word or string more than 25 characters, we can say that insertion and find is actually constant time. So for storing strings, they're pretty darn good. To remove a string from the trie, all we have to do is remove the unique suffixes of the string. In this case, the unique suffixes are E and D. So again, we just iterate through the word we wish to remove, map it to a path in the trie, and then check whether we can safely remove the nodes. In this case, nothing depends on D, so we can remove it. We go up to E, and again, see that nothing depends on E. We can remove it. We go up to N, and then see that N completes the string listen. So we're not going to remove that from the trie. So in this case, to remove the string listen from the trie, all we have to do is get rid of 2 nodes. It's a very quick operation. That ends part 1, and I want to go to part 2. I'm not going to dwell very long on the code. It's a very simple code, and if you want the code, just ask me for it. The implementation of a trie is pretty straightforward, at least a simple trie like I showed you. It's a tree structure, and so it's going to be implemented like any other tree structure. We're going to have a trie node constructor function. It's going to take a value, and it's going to take a set of pointers to any dependent nodes. That's what this .children is. And then it's going to take a flag indicating whether the node completes a string in the trie or not. That's what this .completeString is. So Find is pretty simple. We just iterate through the word. One for loop will do the trick. Insert looks pretty much the same as find. It's a very simple operation. The only thing that's complicated is the remove method, and that's only because there are some funny cases we need to pay attention for, like when we can't remove any character from the string or all characters of the string. But again, it's very simple. You see just a couple for loops and it gets the job done. I hope that introduced you well enough to the concept of a trie, and I want to go on to something a little advanced called Burstsort. Burstsort is a sorting algorithm, and its claim to fame, I'm quoting from the inventors of the Burstsort sorting algorithm, is that it was about as fast as the best algorithms on smaller sets of keys, about 100,000 strings, and is the fastest by almost a factor of 2 on larger sets. And it shows much better asymptotic behavior than any other algorithm for sorting strings. The Burstsort algorithm takes advantage of a trie, which is pretty understandable. After all, tries can be configured to store strings already in order. They have an insertion time, which approaches constant time, and a depth-first in-order traversal will allow you to pull out strings alphabetically. What the Burstsort algorithm uses, though, is not the kind of trie that I showed you previously. It uses what's called a burst trie, which is depicted here. Here you see the term burst trie, which contains the strings bat, bark, barn, bites, wane, way, and west. It looks a little intimidating, but it's not all that complicated. There are really only 2 structural components to this data structure. You have, in the first place, trie nodes, whose values are arrays of alphabetic characters. And then you have these arrays, which are called containers. These arrays have a predetermined size, and when they get overloaded, they burst into new trie nodes and then new containers. The real cleverness of this is this burst trie is that it's division of labor between trie structures on the one hand and arrays on the other. Suppose, I'm going to point briefly at the screen, I know it looks weird. We wanted to install the word wayward into this trie, and we were only using tries to do so. We would have to create 7 layers of trie structures, each of which is an array of 26 characters, just to store one word. If we wanted to store, in addition, the term Western, we would again have 7 trie nodes that we'd have to unlock, each of which is an array of 26 characters. And these trie nodes actually branch out from each other. So to store these extra long strings like wayward and Western, we get a kind of unruly, multiple, like just a large number of trie nodes with characters that don't point anywhere and serve any purpose. So searching through them would kind of be complicated and inefficient. So what it does is it takes all of the common prefixes of all these terms and it puts all of them into trie structures, and it takes all the rare uncommon suffixes and drops them into arrays. I hope this is kind of clear. I'm getting some, Gabe says it's okay? Great. All right. Then what the Burstsort does is it begins by sorting the arrays on the bottom. Since the arrays in this case are going to be small, relatively speaking, we can use some simple algorithms like quicksort or insert sort to very effectively sort those array structures. Then, once those are in order, we use an in-order traversal and just move across the top trie, pulling out strings as we go. The amazing thing is that ordering strings using this data structure yields a linear time complexity, which is really darn fast when you think about it. That's all I wanted to say about Burstsort, not getting into the details of the algorithm. And the takeaways of this are, in the first place, if you're going to use strings or working with sets of strings, consider implementing a trie. It's pretty simple to implement. Second, know the relative strengths and weaknesses of your data structures. Using an array to store many things is unruly, but at the same time, using a trie to store many things can be unruly. The lesson of the burst trie is that we can divide up the labor and really maximize the strengths of our data structures. And then the third, of course, is don't be afraid to combine data structures. You've already done this with the hash table where you have an associative array combined with a linked list. Well, I just showed you a case with a trie combined with an array. So be brave going forward, and thank you for listening.